Okay, up till now, we've talked about how cognitive processes are involved in social interaction, because that's what the course is about. But the question arises from time to time, what's going on in the brain when we talk about these social cognitive processes? And that's what we want to talk about a little bit this week. To begin with, let's just talk about the different levels that we can use to analyze any kind of behavioral phenomenon. This course is focused on what is called the psychological level of analysis, which analyzes mind and behavior at the level of the individual's mental structures and processes. How is memory organized? How do we learn things? What are the basic processes in perception? Other social sciences, like sociology and political science and economics and anthropology, for that matter, don't really focus on this level of explanation. They don't talk about the individual as such, and they certainly don't talk about the individual mind, but rather they try to explain behavior in terms of larger social and cultural processes that take place in the world outside the individual. So if you ask a sociologist to explain something, what he or she will probably do is refer to things like social status or class structure. If you ask an economist to explain something, he or she will probably refer to things like demand curves and market forces and all of that kind of stuff that aren't part of an individual's mental life. Similarly, if you ask a biologist or a chemist or somebody like that to explain behavior as a chemist or as a biologist, what they'll do is they'll give you an explanation in terms of some kind of biological process. They'll talk about genes, they'll talk about hormones, they'll talk about neurotransmitters or something like that. Things that don't have status as mental processes. All right, they go on within the individual, but they go on within the individual mind, within the individual brain and body. Now, what we want to think about doing right now is how to connect these levels of analysis. And a framework that I like for this a lot looks something like this, where we've got these kind of very large-scale level of analysis, the sociocultural level of analysis. At one end, the small-scale biophysical level of analysis at the other end, and the psychological level of analysis that kind of connects them. If you think about it for a second, the reason your genes or your hormones or your neurotransmitters make you do what you do is that they help you to think what you think or feel what you think, to feel what you feel. So processes at the biophysical level of explanation actually are mediated by or have a pathway through the psychological level. And if you think about it, the same kind of thing occurs at the sociocultural level of analysis. It's really not enough to say, well, he did this because he's a high-class person or because of market forces. The individual's behavior always has to be explained in terms of the individual's mental states, and so these sociocultural processes are filtered through the individual's mental processes. Nevertheless, various fields in psychology serve as bridges between psychology and these other areas, between the psychological level of explanation and other levels of explanation. And I take it as the particular task of social psychology to connect the psychological level of explanation to the sociocultural level of explanation. And it's a particular task of things like cognitive psychology and cognitive neuroscience to connect the psychological level of explanation to the biophysical level of explanation. Now, what's happened is, over the last couple of years, there has developed, the last 10, 15 years, there's developed a new field which is sometimes called social neuroscience, which attempts to do for social psychology and the sociocultural level of explanation what cognitive psychology and especially cognitive neuroscience has done for cognition, which is to connect up these levels of explanation and find out exactly what the brain is doing when we engage in various aspects of social interaction or social cognition. One more feature of terminology here before we go on. Just want to point out that you'll notice that I'm talking about social neuroscience right now, but the title of these lectures is social neuropsychology. And the reason for that is I actually don't like the term social neuroscience very much for reasons that we'll talk about in a minute. I'm a psychologist, okay? And I'm devoted by profession to the psychological level of explanation. And for me, neuroscience really is the science of neurons. And if you want to find out how neurons work, then you can be a neuroscientist. But if you want to find out how the mind works, well, you got to be a psychologist of some kind. And what's nice about neuropsychology is that psychology stays in the topic, okay? So that we're always thinking about the neural bases of psychology. With respect to neuroscience, however, there is a very interesting kind of historical or evolutionary tale to be told. Neuroscience itself is a very recent term. It was only entered the lexicon about 1963. Before then, there was really just neurology, a medical discipline that was sometimes decomposed into neuroanatomy, the study of brain structure, the structure of the nervous system, and neurophysiology, trying to figure out how these structures actually work. When neuroscience became an academic field, an interdisciplinary field, beginning in the 1960s, there wasn't anything like social neuroscience. There wasn't even a cognitive neuroscience. Neuroscience came in three flavors. Molecular and cellular neuroscience was really interested in how things work at the level of the neuron. We're interested in aspects of how neurons function as cells and how neurons communicated with each other, synaptic transmission and all of that kind of stuff. The second branch of neuroscience was called systems neuroscience, which attempted to take a kind of step back for a second and look at how the nervous system operated as a system, not at the level of individual cells or even of tissues, basically how the various parts of the nervous system were connected up. And then there was a field called behavioral neuroscience, which was really interested solely in the mechanisms of sensory mechanisms, okay? How does vision work and how does the hearing work? And also interested in the biological motives, research on the biological mechanisms of things like hunger and thirst. This behavioral neuroscience more recently kind of differentiated itself into a whole bunch of different neurosciences. The first of these is known as cognitive neuroscience, which looks at the neural substrates of cognitive processes like perception and memory and thinking. More recently, we've seen the emergence of an affective neuroscience, which tries to do for the emotions what cognitive neuroscience is doing for cognition, to look at the biological substrates of emotional feelings and mood states. If you're thinking about the Kantian trilogy of mind, there isn't a conative neuroscience yet. There isn't a real neuroscience of higher level motivational states, but there is coming onto the scene now a full-fledged social neuroscience, which tries to look at social cognition and other aspects of social interaction and look at their neural substrates. All of these are kind of offshoots of what's known as integrative neuroscience, which tries to fuse the micro and the macro, the clinical and the laboratory and all of that into a full-fledged view of the brain in action. So as I say, what we're going to focus on here is what's sometimes known as social neuroscience. And it turns out that there's actually been a fair amount of progress, especially recently, in trying to understand the neural bases of various kinds of social cognitive processes. The story begins with a case in the 19th century called Phineas Gage, about which you all must know. but I'll talk about it a little bit in a minute because there are some aspects of the Gage case that you probably don't know. But really, the beginning in the 1950s and 1960s began with the study of neuropsychological cases, that is, cases of individuals who had suffered brain damage of some form, insult, injury, or disease affecting some portion of the brain, and who, by virtue of this brain damage, had lost various kinds of various aspects of functioning. More recently, the analysis of neuropsychological analysis of cases of brain damage has been supplemented by the use of brain imaging methods like PET scanning or fMRI is all the rage now. And that if you had to really say what differentiates neuropsychology from cognitive neuropsychology from cognitive neuroscience, it would really be, I think, the reliance on these brain imaging methods, and they're going to be the focus of most of what I talk about today. There is a deep and abiding sense in psychology and in cognitive science that somehow neuroscience is going to solve all our problems, that somehow neuroscience is going to tell us how the mind works, and everything's going to be wonderful. We're going to get a lot out of neuroscience that we have been missing just with our abstract analyses of nodes and associative networks and parallel distributed processing and all of that kind of stuff. I'm here to tell you that neuroscience is not going to solve the problems of psychology and cognitive science. That is a false and vain hope. False hope on the part of those of us who are not neuroscientists, a vain hope on the part of those of us who are. For the simple reason that cognitive, social, affective, conative neuroscience, any kind of neuroscience that tries to understand what the brain does as opposed to how the brain works, depends for that explanation on the existence already of a valid psychological theory. You simply have to know what the mind does. You should pardon the dualism here. You have to know what the mind is doing before you can figure out how the brain does it. Here is a couple of examples of major figures in the field who think that somehow neuroscience is going to solve the problems of psychology and cognitive science. John Cacioppo, who deserves recognition as the guy who founded the field of social neuroscience, beating Stan Klein by 4 crummy years. But in a very important early paper from 1992, asserted that knowledge of the body and the brain can usefully constrain and inform concepts and theories of psychological function. That is the basic assertion of cognitive and social neuroscience, that knowing how the brain works is going to tell us something of importance for psychological theory. More recently, Kevin Oxner and Matt Lieberman, who are kind of second-generation social neuroscientists, in an important paper, drew an analogy between the prospects for social neuroscience and what they thought they saw happening in cognitive science. They argued that cognitive psychology underwent a transformation as data about the brain began to be used to constrain theories about cognitive processes. This is a viewpoint that I call the rhetoric of constraint. The idea that somehow knowing how the brain works is going to constrain theories at higher levels of analysis is a rhetorical twist that you will find running through a lot of cognitive and social neuroscience, and it is a rhetorical twist that we should regard with some suspicion. Here is a very interesting example of it. It's from Dan Goleman. Many of you know Goleman's work on emotional intelligence. He now is writing books on social intelligence. He's actually a PhD a psychologist who forsook an academic career to make $1 million, first as a science writer for the New York Times, and more recently as a writer of extremely popular books. Okay, In his new 2006 book called The Social Intelligence, he says, new neuroscientific findings on social life have the potential to reinvigorate the social and behavioral sciences. The basic assumptions of economics, for example, have been challenged by what he called the emerging neuroeconomics, which studies the brain during decision making. Its findings have shaken standard thinking in economics. Okay, that is simply not true. Okay, economics is in deep trouble these days because its theories were too narrow, but findings about how the brain works had absolutely nothing to do with it. What shook economics as a discipline was the emergence of a psychology of decision making. Herb Simon won the Nobel Prize for Economics not for doing research with some kind of brain imaging device, but for sitting in boardrooms and looking at how corporate managers made decisions. That's where Simon got his Nobel Prize. Danny Kahneman and Amos Tversky. Kahneman got the prize. Tversky died before he could get it as well. Made huge revolutionary changes in our understanding of economic theory by administering paper and pencil tests to college sophomores. They never did any brain imaging either. The major advances in economics that Goldman touts here were not made by neuroscientists. They were made by mere mortals, people like us who administer, who collect observational data and administer various kinds of experimental tasks. So the argument here is that although some people assert that somehow neuroscientific findings will contribute to psychological theory by constraining psychological theory, there's absolutely no reason to think that that's going to happen. Here's the famous example. It is often claimed that studies of patient HM and others like him who sustained damage to the hippocampus and other structures in the medial temporal lobes of the brain revamped totally our understanding of the structure of memory. There's the hippocampus right there. If you draw it right, it looks like a seahorse, which is where it gets its name. It's buried right there in the medial portion of the temporal lobes. And as you'll remember, HM suffered damage to his hippocampus and some related structures and lost the ability to remember new things. The fact that we discovered that the hippocampus is critical for memory had absolutely no impact on our psychological theories about how memory works. And the proof of this is that if you trace the history of people's attempt to explain the role of the hippocampus, those explanations track and follow advances in the psychology of memory. So when HM was first studied back in the early 1950s, we didn't have a theory of memory. All we had in psychology was a theory of learning. So Scoville and Milner said, well, the hippocampus is somehow critical to learning. In the mid-1960s, psychologists made a distinction between two forms of memory, short-term memory and long-term memory, and immediately the interpretation of hippocampal damage changed so that what people said was, well, the hippocampus is important for long-term memory, but it's not important for short-term memory. A little bit later, the psychology of memory produced a distinction between the encoding of a memory trace and the retrieval of information from memory, and the interpretation of hippocampal function changed immediately so that people said, well, the hippocampus allows you to encode memory, but it doesn't allow you, the hippocampal damage prevents you from retrieving memories that you've encoded. Later on, the short-term versus long-term distinction was replaced by a levels of processing approach to memory, and the interpretation was that the hippocampus is required for deep processing of stimulus information leading to long-lasting memory traces, and all the way down. In each case, the interpretation of hippocampal functioning followed an advance in psychological theory. It didn't precede it, it didn't constrain it, it didn't stimulate it, it didn't do anything. people said, oh, the distinction between procedural and declarative memory, that's a really good distinction. Hey, now let's go back and look at HM and see if he's got one or the others of these. And lo and behold, HM had impaired declarative memory, but not impaired procedural memory. But the brain damage itself and the brain damaged patient itself didn't do anything to constrain theories of mental function. It just doesn't work that way. The point of this is that neuroscience is great. Cognitive neuroscience is great. Affective neuroscience is great. Social neuroscience is great. But we need to understand that, as someone once said, that someone being me, neuroscience without psychology is just neuroscience, okay? Without psychology, you can figure out how the nervous system works as a biological system. You can find out how axons are connected to cell bodies leading to terminal fibers, and you can find out all about depolarization, and you can name all the neurotransmitters. But if you want to find out what the brain is doing, you have to already have a valid psychological theory that allows you to interpret the brain function. Put another way, unless the psychology is already right, the neuroscience has got to be wrong. If you want to think about neuroscience as encompassing things like mental functions, cognitive functions, affective functions, and so on. If you don't already know, again, pardon the dualism, what the mind is doing, you're never going to figure out how the brain does it. Okay, so enough of that sermon for a moment, though we will come back on Wednesday to some examples that shows you just how critical the psychological theory is to the interpretation of neuroscientific data. Okay. In physiology, in neuroscience, and for that matter in psychology, there have historically been two quite different views of brain function, two quite different views of how the brain works. Until relatively recently, the general view was that the brain served as what you might call a general purpose information processor, that what the brain did was allow us to learn. And we thought about learning in terms of the formation of associations, and so most of the brain was devoted to forming associations of various sorts. Gradually, as neuroscience has come alive, this idea of the brain as a general purpose information processor has been supplanted by an idea of by what's called the doctrine of functional specialization. The idea that various parts of the brain are dedicated to various psychological functions. That the brain doesn't work just as a whole unit, okay? The way a sponge works as a whole to absorb water. The old idea was that the brain kind of worked as a sponge to absorb associations, to form associations. Now we have quite a bit of evidence for what's known as localization of function, arguing that there are discrete modules in the brain or systems of modules, pieces of the brain or systems of pieces that are dedicated to various functions. Here's an illustration of this kind of change. I took the introductory psychology course in 1967, and this was the diagram of the brain in my textbook at the time. Yes, I saved my textbooks. And this is what people thought the brain looked like. There was an area of the brain that processed auditory stimuli, and an area of the brain that processed visual stimuli, and up here there was an area of the brain that organized motor behavior, and another area of the brain that processed bodily the stimuli, and that was it. What's the rest of the brain for? The rest of the brain is called association cortex. And what people thought was all it did was form associations, right? That was the view of of the brain at the time. Gradually, however, as I say, this view of the brain as a general purpose information processor was supplanted by what has come to be called the doctrine of modularity, a term that comes to us from a philosopher, Jerry Fodor, who argued that instead of being one big thing, one monolithic structure kind of sitting on top of the spinal cord, the brain actually consisted of a number of task-specific modules. Now, the doctrine of modularity argues that modules have lots and lots and lots of different properties. I don't want to deal with those with all those right now. There are really only 2 or 3 of these that are important to us at the moment. The first of these is that these modules are domain-specific. Fodor argued that you had a module that handled language, and you had a module that was different from the module that handled visual perception, and you had a module for visual perception that was different from the module that handled auditory perception, and so on. These modules were informationally encapsulated, which meant that they weren't much affected by what was going on elsewhere in the brain. They took inputs and generated outputs, but they were pretty much isolated from each other. And then finally, Fodor argued that these modules, each of them was associated with what he called a fixed neural architecture. That is, that there was some piece of the brain that was a physical implementation of each of these cognitive modules. And what happened was Fodor's doctrine of modularity gave neuroscience a task. If you think about it for a second, if the brain is really just a general purpose information processor, and all it does is form associations between stimuli and responses, which is what we thought the brain did as recently as 40 years ago, that's not very interesting. Okay, you really don't have to. That's it. That's the answer, right? You don't have to think about the brain anymore than that. What the doctrine of modularity does is to give cognitive, social, and affective neuroscience a task to do, which is to say, look, what you've got to do is you've got to find where these particular modules are in where these modules are in the brain. And again, if you think about it for a second, you can't find modules in the brain unless you know what the modules are. You can't find something unless you know what you're looking for. So you got to have the psychological theory first that specifies what these modules might be so that you can develop tasks to tap into these modules and then see them somehow in the brain. So when Fodor was talking about modularity, yeah, he was talking about modules devoted to language and visual perception and motor behavior and stuff like that. But the question arises in a course like this, maybe there are modules for various aspects of social cognition. Maybe there are discrete pieces of the brain or larger systems of brain pieces that are specifically dedicated to various kinds of social tasks. And if we use neuropsychological methods studying people with brain damage, or we use brain imaging methods looking at the intact brain as people perform various kinds of tasks, we can find out where in the brain these modules are located. Now, the doctrine of modularity is relatively recent, Fodor, 1983, but of course its roots go way back to the 19th century and to a pseudoscience. We now recognize it as a pseudoscience known as phrenology. Gall, Spurzheim, and other 19th century neurologists, some other 19th century neurologists, argued that mental life was mediated by a series of faculties, affective faculties regulating our emotional life, intellectual faculties regulating our cognitive life, and that each of these mental faculties was associated with a specific part of the brain. Now, in the definitive statement of phrenological doctrine, there were 35 of these these faculties, just 35, not 34, not 36, but 35 aspects of mental life. And Gall and Spurzheim argued that, in principle, we could figure out where these were in the brain, and in fact, they localized them, or thought they did, using methods that seemed like a good idea to them at the time. Basically, by taking people who either had a lot of some ability or not too much of some ability, and then feeling their heads looking for bumps and crevices. Okay? The idea was that if you had somebody who had a really good sense of musical, really high levels of musical ability, and you found a bump on their head, well, that meant that there was a lot of brain tissue under there, and so that must be the music area. If you had somebody who couldn't play the piano worth a damn, you could feel around on their skulls and find a dent on their head, and if you found a dent on their head, that meant there wasn't very much brain underneath there, so that would just kind of confirm that that was the musical area. This, of course, is a complete crock, okay, to use a technical term, but that's what they did, okay? They didn't have magnets, they didn't have all the tools we have today. They did this stuff instead, and so they found that here was a center that mediated the faculty of cautiousness, and here was a center that mediated the faculty of friendshipness, and here was a center for combativeness, and so on and so on and so forth. That's basically what they did. Now, what's really interesting, I think, historically about phrenology is that more than half of the 35 phrenological faculties were expressly social in nature. They had their fundamental purpose, if you will, had to do with things like personality and social interaction, not with thinking or reasoning. Here's a list of that's like, I think there are 18 or 19 of these here, and if you correlate these with the postulated loci in the brain, you can see that most of the brain's a social brain. Yeah? Because the purely cognitive functions are associated with these relatively small areas up here, what we would now call orbitofrontal cortex. But most of the brain, as far as the phrenologists were concerned, that had to do with the social cognition. Well, that's just kind of a historical footnote. Where does any of this really come from? We know that this is pseudoscience. Well, it turns out that, again, beginning in the 19th century and stimulated mostly by the phrenologists, early neurologists actually began to discover certain parts of the brain that did seem to be involved with various kinds of the specific psychological functions. The first of these was a neurologist named Broca, who had a patient named Tan, that was his nickname, who had what's now known as an expressive aphasia. He couldn't speak. He actually could only utter one syllable, the syllable Tan, which is how he got his name. Broca waited for Tan to die, then went in, autopsied his brain, and discovered that Tan had a huge lesion in a part of the frontal cortex, which is now known as Broca's area, and that was the very first scientific documentation of a specific part of the brain being associated with a specific specific psychological function. A little bit later on, another neurologist named Wernicke had another patient who had problems understanding language, waited for him to die, autopsied his brain, and discovered that he had a lesion in a very different area, not in what we call Broca's area, but now in Wernicke's area. 1860, 1874, the first scientific evidence for something like the localization of function in the brain, the first evidence that really supports this so-called doctrine of modularity. What's interesting here historically is that there was another case in the 19th century which, had it been analyzed properly, actually would have beaten both Broca and Wernicke to the punch, and that is the famous case of Phineas Gage, studied by a New England physician, John Martin Harlow. Is there anybody here who doesn't know the story of Phineas Gage? Okay, he was a railroad worker. He was setting some explosives. The explosives went off before they were supposed to, and what happened was his tamping iron entered his cheek, went behind the eye, and right out the top of his head. This is a drawing of Gage's skull with the tamping iron placed in it. If you want to know what the tamping iron actually looked like, here he is. This is Phineas Gage. People have probably never seen what Phineas Gage actually looked like. This is what he looked like. You can see his one eye is closed because the tamping iron did some serious damage to his eye. That's the tamping iron. It was almost 5 feet long. It's some huge piece of metal that went through this guy's head. And what was amazing about it is that he survived at all. He did, in fact, survive. Even though he went through by accident what we would now call a near total frontal lobotomy. There it is. That's the newspaper. This is the newspaper the report of Gage's accident. And what's interesting about this early report is that what people were just amazed about was that he lived at all. Okay, but Gage became more important later on because his physician, John Martin Harlow, wrote a kind of retrospective account of the Gage case, in which he argued that after the accident, Gage's personality had changed. Okay, in this regard, his mind was radically changed, so decidedly that his friends and acquaintances said he was no longer Gage. The Gage that had been a very upright citizen of Cavendish, Vermont, was now, Harlow said, now kind of a reckless person who was very cordial, was now more aggressive, a person who was very cautious in his words, now used a lot of profanity. And Harlow speculated that what had happened was that this accident had damaged particular parts of the brain which the phrenologists understood to be associated with particular functions. So before, he was efficient and capable, he was shrewd and smart, he was energetic and persistent. Afterwards, we were told he was fitful and capricious and impatient and obstinate and lacked deference and all of that business. And what was interesting about this was that the phrenologists of the time said, well, that's exactly what you'd expect because look where the damage was. The tamping iron came out right there, right in the junction of benevolence and veneration, right? The two parts of the brain that are supposed to mediate benevolence and veneration, they were destroyed. So of course, Gage was no longer Gage. He used to be like that. Now he's like that. Okay, historical footnote here. It's very important for people to understand that the evidence for this is a famous case. It's written about all the time. It's referred to all the time in the literature. But in fact, we know very little about what Gage was really like after his accident. Okay, not least because Gage eventually left New England and actually moved here to the Bay Area and took up work. Remember where his accident was? His accident was in 1848. What happens in 1849? The gold rush, okay? Like everybody else in New England, he wanted to get rich, so he came here. And in fact, Gage was gainfully employed for a period of roughly 10 years, first in Santiago, Chile, because he went around the Horn, ran out of money, worked in Chile for a while until he could make enough money to get up to San Francisco. When he died, he was buried in Laurel Hill Cemetery, where UCSF has a building now. And when all the cemeteries were moved out of San Francisco after the earthquake, his body was moved to Colma, where everybody else's bodies were moved to. And if you go to the Pioneers Monument in the cemetery of Colma, you can see Gage's name. Okay, it's such a famous case. How come? And it was 1848, 1849. He died in 1859. That's still before TAN. How come? How come TAN is the index case for the doctrine of of modularity and not Phineas Gage? The reason is we don't have Gage's brain. All we have is Gage's skull. Nobody in San Francisco, when he died, nobody in San Francisco knew that he was anybody special, right? So they didn't preserve his brain the way Tan's brain was preserved, so it couldn't be looked at by other people. All we have is Phineas Gage's skull, okay, which is that, okay, with the hole in the top, and that just wasn't good enough. The neurologists at the time, who were really beginning to test phrenological doctrine, needed to see the brain, not just the skull, to see where the damage really was. The other thing that needs to be understood about the Gage case is that John Martin Harlow, the physician who had treated him and who reported that Gage was no longer Gage after his accident, and who diagnosed his personality problems, was himself a closeted phrenologist. Okay? So Harlow knew where the damage was, knew what phrenological doctrine said was being mediated by those parts of the brain, and it's entirely possible that Harlow's knowledge of phrenological doctrine influenced his interpretation of Gage's behavior. So it's just not a very good case for most purposes. But the fact of the matter is that I think that Gage, in the same way that somebody like Tan or maybe patient HM is the index case for cognitive neuropsychology, the guy who really got cognitive psychologists thinking that there might be particular modules of the brain associated with particular cognitive functions. Even though the case is very, very, very ambiguous, I think the Phineas Gage case deserves to be understood as the index case of social neuroscience. Maybe it's true, maybe it's not true, but it was the Gage case that gave us the idea that there might be particular brain modules associated with particular aspects of personality and social interaction. Fast forward 150 years, okay? What do we think about this now? Well, beginning in the 1980s, a number of psychologists and others who are interested in neural functioning began to discuss the possibilities that there were particular parts of the brain that were associated with particular social functions. The first guy to do this seriously was Howard Gardner, which many of you will know from his famous theory of multiple intelligences. Gardner argued that intelligence was not just one thing, but there were 6 or 7 different kinds of intelligence that could be dissociated from each other, so that you could be high on one and low on others and so on. And Gardner argued that among these multiple intelligences was an intrapersonal intelligence that had to do with a person's ability to understand his or her own interior life, especially emotional life, and an interpersonal intelligence, an ability to deal with other people, to notice and make distinctions among other individuals. Gardner argued that these multiple intelligences could be identified by what's known as converging operations. You take different kinds of data and they will converge on the existence of various kinds of the intelligence. And for our purposes today, one piece of data that Gardner relied on was the idea that these various kinds of intelligence could be isolated by brain damage. This is a standard neuropsychological idea that brain damage to particular parts of the brain can knock out certain kinds of functions. And Gardner argued that you could isolate intrapersonal intelligence from the other forms of intelligence and interpersonal intelligence from the other forms of intelligence by looking at people who were brain damaged, like HM, even like Phineas Gage, even if the Phineas Gage case itself we now know to be kind of ambiguous. Gardner did look at the Phineas Gage case, but he also argued that there were certain forms of brain disease, Pick's disease, and especially what we now know as frontotemporal dementia, a form of dementia that's studied by Professor Bob Knight here at the Berkeley campus, seemed to impair social functioning at the same time as they spared cognitive functioning. Okay? At the same time, there are other neurological illnesses like Alzheimer's disease and Down syndrome, which appear to impair cognitive functioning but spare social functioning. Okay? The idea that you could dissociate cognitive functioning from social functioning, impair one but spare the other, whichever one you want to do, suggests that cognitive functioning and social functioning are mediated by separate sets of brain structures. And the idea for social neuroscience really comes from here. Okay, a little bit more recently, Ray Jackendorf argued that there are separate faculties of social cognition that are separate from kinds of non-social cognition. So we suggested that we have particular cognitive modules, like the modules that are involved in language processing or visual information processing, that are specifically oriented to answering questions like, who is it, and what's this person doing, and what's this person doing to me, and so on. Okay, we're going to skip this for the purposes of getting through this. Simon Baron-Cohen, we'll talk about him more next week, had a similar idea around in the early 90s, looking at cases of autism and arguing that patients with autistic spectrum disorders had specific deficits in social functioning, which suggested that whatever the brain damage was that was involved in autism, Baron-Cohen didn't know what it is. We still don't know what it is. But whatever the brain damage is seems to affect social functioning more than other kinds of functioning. Again, this is an argument for the modularity of social cognition. And then finally, Dan Goleman himself, however wrong he may have been about the rhetoric of constraint, argued that there were particular functions, the social cognitive functions, that he thought were mediated by by different brain structures. So primal empathy, the ability to feel what somebody else is feeling, the ability to listen to somebody and actually communicate with them, the ability to influence others, the ability to synchronize your behavior with somebody else. Goleman argued that these were the very likely kinds of things to be associated with various modules in the brain. Okay, so here we have first Phineas Gage and cases of brain damage give us the idea that it really might be true that various social cognitive functions might be mediated by brain structures, brain systems of brain structures that are different from those that mediate non-social cognition. And people like Ray Jackendorf and Dan Goleman suggesting what those structures might be, okay? So here we have the theory leading, the psychological theory leading the neuroscience. The question is, where are they? Where are these brain structures? What aspects of social cognitive function seem to be mediated by separate modules in the brain? That's the problem we'll take up on Wednesday, and as you'll see, that is not so simple a question to answer. Thanks very much. We'll see you on Wednesday.